So in this video, we're going to be looking at structural isomerism. Now, structural isomers, we say that they're compounds with the same molecular formula, but with different structural formula. There's three different types of isomerism we need to be aware of. There's chain isomerism, positional isomerism, and then functional group isomerism as well. We need to be able to memorize these and apply them to different exam questions and different molecular formula. Now, how do we actually check if two molecules are going to be isomers of each other? Well, what we would need to check for is, first of all, do they actually have the same molecular formula to begin with? And then, of course, if they do they have different IUPAC names, which will tell us if we've got different structures? Now, looking at our first example, we're going to look at chain isomerism, and chain isomerism is when the carbon chains can be either branched or unbranched, in other words, in a straight chain. Now, you can see over here, I've got a molecule of pentane with the formula of C5H12. Now, this is going to be a straight chain isomer with that molecular formula. And let's say if I were to grab one of these carbon atoms, let's say this one over here, and move it to this position over here, what I would end up forming is my longest carbon chain being butane, a methyl group at the 2 position. I actually have a compound that is now going to be called 2-methyl, and then it's going to be, of course, butane. Now, this still has a formula of C5H12, so we know, of course, 2-methyl butane is going to be a structural isomer, a branched chain isomer with a molecular formula of C5H12, so it's a branched chain isomer of pentane. Now, let's say if I were to grab another methyl group, and let's see if I were to grab this one over here and move it over here, what I can actually end up with is the following compound that looks like this, and that's going to be, of course, having a name of 2,2-dimethyl, and then, of course, it's going to be propane because the longest carbon chain is now 3. Now, this also has a formula of C5H12, so we know, of course, this is going to be an isomer because it's got the same molecular formula but a different structural formula. And really, these just come by trial and error, and you're just going to work out how many different types of isomers you can actually get by drawing them out and then naming them. Now, let's say if I were to grab something like, let's say, this carbon atom and move it to this position, how you can actually tell if you don't have an isomer is of course, you draw it out. If you end up with the same name as before, following our IUPAC rules, you wouldn't actually end up with an isomer. So yeah, let's take this carbon atom and move that to this position over here. I would end up with 1, 2, 3, 4 carbon atoms, and then I would add the methyl group to this position. Because, of course, the longest carbon chain now is going to be 1, 2, 3, 4, 5 carbon atoms, we would actually still call this one pentane, so we know we don't have an isomer with this one. So yeah, you can see over here how we can tell if something's going to be an isomer or not, and again, it just comes with trial and error. Looking at the next one, we've got positional isomerism. If we're dealing with positional isomerism, all we're doing is we're taking a functional group and a branch, and we're moving the position of it. You can see here I've got butane 1-ol with an alcohol at the 1 position, and what we can actually do is we can move that alcohol group and we can actually move it to the 2nd position, so we end up with, in this case, a structure that is going to be called not butane 1-ol, but instead it's going to be butane, and then it's going to be 2-ol itself. I've still got the molecular formula of C4H10, and then it's going to be O. I know I've got the same molecular formula, different structural formula. I know it's going to be, of course, a isomer, a positional isomer in this case. Now, what about if I were to move it to the 3 position? Well, again, this is a common mistake and it comes down to trial and error. Well, I can actually end up with 1, 2, 3, 4 carbon atoms. I'm going to end up with an OH over here. Well, if we follow our IUPAC, we actually end up with, in this case, butane 2-ol. So if I were to compare that to the original butane 2-ol over here with a molecular formula of C4H10O, it does have the same molecular formula, but it doesn't have a different structural formula. So we know this isn't going to be an isomer. Now, again, you can actually get a mixture of positional and chain isomers in this example, but of course we're not going to do that. We're going to deal with them separately. Now, moving on to the harder one, if we're dealing with functional group isomerism, this is normally when, of course, our functional group can change altogether. You can see here I've got an aldehyde with the formula of C3H6O. It's an aldehyde because it ends in anal, and the carbon-oxygen double bond is going to be at the end of the carbon chain. Now, I can actually move the position of that, so I end up with a ketone, and that ketone is going to have, of course, a carbon-oxygen double bond not at the end of the chain. And in this case, I've actually got the ketone, which is going to be propan 2-1, but of course, because it can only be at the 2nd position, we just say propanol. So yeah, it's still got the formula of C3H6O. We've got the same molecular formula but different structural formula. Now, we can't actually end up with anything else. If I were to move this functional group to, let's say, something like this, to the position over here, which is going to be the 3rd position, right, we've still got got over here propanol. It's still going to be, of course, the same molecular formula, but we've also got the same structural formula compared to this original example itself. So this isn't going to be an isomer. Looking at the next one, if I've got an alkene, a rule to remember is for every carbon-carbon double bond, you can actually form one ring structure itself. If I've got a carbon-carbon double bond here, I can actually change the functional group while having the same molecular formula, and I can actually end up with a cyclohexane molecule. You can actually make cycloalkanes from alkenes, and that's an example of a functional group isomer. This one is going to be called, of course, cyclohexane following IUPAC. We've still got the formula C6H12, so we know it is going to be an isomer. So yeah, we can also get positional isomers here and then chain isomers as well. We can actually get a chain isomer of the cycloalkane where we can end up with something like cyclopentane with a methyl group hanging off, because that still has the formula of C6H12, and then of course it's going to be called methyl and then cyclo, and then it's going to be pentane itself, and there's that one done too. But yeah, this isn't a functional group isomer, this one's more of a chain isomer. So yeah, there's that example there. I am going to move the C6H12 away just because it kind of looks like it's attached to the cyclopentane itself. But yeah, if I were to look at the next one, you've got here a carbon-carbon triple bond. Now when you deal with carbon-carbon triple bonds, we actually call these functional groups alkyne groups. The homologous series is going to be the alkynes, and if I've got a carbon-carbon triple bond, right, we can actually translate that and we can actually end up with an isomer where we actually change it into a diene, where I've got 1, 2, 3, 4, 5 carbon atoms, an alkene at position 1, alkene at position 3. I can actually call this molecule pentane because it's still got 5 carbon atoms, and then it's going to be 1, 3, and then diene itself. So yeah, we've got 2 double bonds over here. We've got a diene, 2 alkene groups, that makes a diene, and it still has a formula of C5 and then H8 itself, so that is an isomer. Now if you were to look back at this idea of having a carbon-carbon double bond, right, we know that's going to be equal to 1 ring, so I can actually sacrifice one of these carbon-carbon double bonds, and I can actually end up with a cycloalkene in this case, which is a harder one to spot. So I can actually end up with cyclopentene, which of course if we were to name it, we would end up with cyclo and then pentene itself with a formula of C5H8. So we know, of course, this is also going to be an isomer. Now an even harder one is if you were to think 1 carbon-carbon double bond is 1 ring, 2 carbon-carbon double bonds can actually get you 2 rings, and you can actually end up with the following bicyclic structure over here. And this one, I'm not going to name it, but of course it still has the same molecular formula of C5H8, but it also has a different structural formula itself as well. So yeah, that goes outside the spec, but of course it's still within the mark schemes of the harder questions with alkynes. Alkynes, I think the last time it came up was 2020 in the AS paper, but of course it is a common question that's come up a few times now. So yeah, moving on, I want you to have got the following task. I want you to give all the structures possible along with the names with the following molecular formula. Pause the video, have a go at the following, and resume once you're ready to go over the answers. So yeah, look at the first one. You've got here 4 carbon atoms, 10 hydrogen atoms. It kind of fits the general formula of an alkane where you've got CN, H2N, and then it's going to be +2. You can think over here that you've got, of course, maybe something like butane for 4 carbon atoms. There's your simplest answer for that one. So we've got, of course, butane as one isomer, and it fits the formula for C4H10. We can also end up with a branch chain isomer where we can end up with 2-methyl, and then it's going to be, of course, propane. And you could, of course, get away with just saying methyl propane because it can only be at one position again. So yeah, there's 2 examples over there. Can't really think of any more. Can't really end up with any functional group isomers or any positional isomers, so that's that one done. The next one, you've got C4H8O, which kind of looks like an aldehyde or a ketone. If I were to go with something like this, I've actually got an aldehyde where I've got, of course, butanol in this case. It matches the general formula of aldehyde, and I also know it matches a molecular formula of course, C4H8O. That's one example there. I can also get a branch chain isomer of this one as well, where I end up with, of course, one of the carbon atoms. This one over here, it's going to be this carbon atom over here. That's going to move over to, of course, this position. So I actually end up with a methyl group here. So I'm going to say, of course, I've got 2-methyl, and then it's going to be, of course, propanol, still an aldehyde. If I were to look at a functional group isomer, I can actually end up with, of course, 1, 2, 3, 4 carbon atoms, and then, of course, a ketone at this position over here, and I can actually end up with butan, and then, of course, it's going to be on could have said butan 2,1 doesn't really matter, and the reason why is because of course it can only end up being in the 2 position for a ketone. Now the thing is, there's a reason why we actually do it that way, and we actually say butan 2,1. Some of you might have actually got butan 3,1, and that's actually going to be wrong. The reason why is because if we were to follow our UPAC nomenclature, we would actually still end up with butanone itself, butan 2,1 itself. Again, remember, you have to name it using our UPAC nomenclature. So yeah, moving on, I've got another task for you to do. Same thing again, pause the video and have a go at the following questions. So yeah, we look at this example. We've got here what appears to be a haloalkane. We've got 3 carbon atoms, 6 hydrogen atoms, and let's say if we were to deal with the alkane propane, which is going to be C3 and then it's going to be HA, we know 2 of these hydrogens has been swapped out for chlorine atoms. I'm just going to suggest a structure to begin with, so I'm going to put both these chlorines at this one position over here, so I can actually end up with 1,1, and then it's going to be dichloro, and then propane, that's my longest carbon chain, 3 prop. If I were to come up with another structure, I can actually end up with, let's say, one of the chlorines in the 2 position. So I can end up with, of course, 1, 2, 3 carbon atoms, chlorine here, and then chlorine there as well. We could actually call that one 1, 2, and then of course dichloro again, and then it's going to be propane. Now another isomer is when I can actually take both of these chlorines and put them at the 2 position, so I end up with 2, 2, and then it's going to be of course dichloro and then propane. So yeah, so far we've got 1, 2, 3 isomers. There is another one that we can get as well, and that last one we can actually end up with 1, 3, and then it's going to be dichloropropane itself. So I end up with 1, 3 dichloro, and then it's going to be propane for that last one too as well. And there's of course 1, 2, 3, 4 isomers that we can get, 4 positional isomers with a molecular formula of C3H6Cl2. Now the next one's quite a straightforward one to see. That one, it fits the general formula of an alkene, where I know of course I've got 4 carbon atoms. The easiest one to do is butanone. But I can also end up with a positional isomer where I end up with, of course, at the 2nd position, so it's going to be butuene. Now you can also get here E and Z isomers, but of course I'm going to be focusing on structural isomerism here, not stereoisomerism. So yeah, we've got butuene. We can also end up with a branch chain isomer where we end up with, of course, 2-methyl. You don't need to put the numbers here, it doesn't really count. And then you end up with prop-1ene, because of course it can only be at these positions. And then another one that you can end up with, remember you've got a carbon-carbon double bond, so that means of course you can end up with a ring structure. You can actually end up with, of course, cyclo, and then it's going to be butane. Now we can also branch this too, so we end up with methyl, and then it's going to be cyclo, and then because the ring contains 3 carbon atoms, we're going to say propane itself. And there's that last one done there.